So this time I'm going to talk about models of words. We had the reading based on the Goldberg book where we trained things using WordDevec. I'm just going to very briefly go through like a summary of the content that we had there, and then I'm going to go into more advanced things. If I still have time at the end and run out of slides, I'm going to talk a little bit maybe about bilingual or multilingual word embeddings, which is kind of an interesting thing this time. But I already have lots of content, so I might not go into that much detail of that this time and leave it for a later class also. So regarding models of words, what do we want to know about words? And there's lots of different things that we could say that we'd like to know. For example, are they the same part of speech? Are they nouns or verbs or whatever? Do they have the same conjugation? So for example, if it's a verb, is it in the past tense? Or if it's a more kind of richly conjugated language, something like Finnish or Russian or something like that, you might have very complicated conjugations. Do these two words mean essentially the same thing? Like, are they the same meaning semantically? Do they have some semantic relation? Like, are they in an is-a relation, a part of relation, a went to school at relation? So you might have Obama and went to school at Harvard or something like that. So there's lots of things that we'd like to know about words. The first two things here are syntactic things. The last two things here are semantic things. And we'd like to be able to handle syntax and semantics or any other type of word, any other type of thing like that as well. So before going into how to learn these with neural nets, I think it's worth thinking about what people did before neural nets or before machine learning methods. And one very, very famous attempt of this is WordNet. How many people have used WordNet in a project or research or something like this? I see about 1/5 of the class or something like this. This number goes down every year, actually. And I think this speaks to the power of word embeddings to some extent. But basically what WordNet tried to do is it's this big database of words that include part of speech and semantic relations like artifact is kind of the top level semantic class, and then you have a motor vehicle is a type of artifact. A motor car is a type of motor vehicle. A gas guzzler is a type of motor car, I guess. So this was a major effort to develop, and there are projects in many, many different languages. They're all linked together, et cetera. But as I said, this is a major effort to develop. And actually, if you go to the WordNet site, or at least if you went there 1 year ago, there was this big thing in red that said, I'm sorry, we don't have enough money to develop this project anymore, so we can't take your requests about how to modify WordNet. So like, this is a very real practical issue that, it takes a lot of money and time to maintain these things. And it's not necessarily possible to do so. So then the question is, can we do something similar and maybe more complete without the manual effort? And an answer to that is word embeddings, which you read about. They're continuous vector representations of words. And within the word embedding, these features of syntax and semantics may be included. So for example, element 1 might be more positive for nouns. Element 2 might be positive for animate objects, and element 3, might have no intuitive meaning whatsoever. You don't know. So one important thing to remember is that these word embeddings encode all kinds of things. They don't just encode semantics. And actually, Zach Lipton, who's also here at CMU, a little while ago, we got in an argument on Twitter about whether it's okay to call word embedding spaces semantic spaces. And I think the answer is the spaces definitely do encode some things about semantics, like relationships between words is kind of the definition of lexical semantics. But they're much more than semantic spaces. They're also syntactic spaces because they encode syntax and they encode other things as well, like maybe sentiment or just peculiarities of usage or whatever. So Word embeddings are cool. This is the obligatory slide where basically you can do king minus man plus woman equals queen. And this is because there's this consistency in semantic space where a vector between two particular did I say semantic space? I meant embedding space, but sorry. There are these consistencies in embedding space where a vector between two word embeddings has some sort of consistent meaning, be it a syntactic meaning or a semantic meaning. So in this case, man goes to woman, uncle goes to aunt, king goes to queen. This is kind of the gender dimension. Or the gender vector, and then you also have the plural vector, which is king goes to kings and queen goes to queens. So you can see that the red vector here is the one that's expressing something syntactic, and the blue one is expressing something semantic. So the interesting thing about this is, like, what is the female equivalent of king is not something that you could do with WordNet. Like, it's just not something that was encoded in WordNet because people never thought of doing this. So these, word embeddings really open you up to a lot of creative things that you could do without, that you couldn't have done in these previous lexical resources. So how to train word embeddings? I think this part was covered relatively well in the reading. But some things that it pulled up were initialize randomly and train jointly with the task, pre-train on a supervised task, and pre-train on an unsupervised task like word2vec. And honestly, the second one is pretty rare. The reason why the second one is pretty rare is supervised training data is very hard to come by, and it's much easier to come by unsupervised data, like lots and lots of textual data that doesn't have any human annotations on it. So it's much more common to do the third one or the first one. And if you think about when are word embeddings useful? Like, what are the big tasks that you've really heard word embeddings help out with a lot? Are there any ideas? Like, has somebody used word embeddings and gotten a really good gain in one of the tasks that they've done before? Yeah.
It was actually trying to model for the question answering task, I believe, and we're trying to do with our presentations on a fairly small corpus, and then embeddings between PubMed were actually very helpful.
Okay. So a question answering task where you had a small corpus of questions and answers in a large PubMed text corpus. Any other examples? Come on, one more. Okay, I'll give an example because people are feeling shy. So the named entity recognition is another very easy example where, or example where these are very useful. So you have a small corpus of entity annotations, people, places, or things, and then you have large corpora from which you train embeddings, and this helps you generalize to lower things. So an example of a place where word embeddings are not necessarily useful is something like machine translation, which is also a task very near to my heart. And the reason why is because actually for machine translation, it's quite easy to get very, very large training data for most language pairs. So if you have 10 million sentences worth of training data for machine translation, actually the gains that you get from embeddings are quite small. So the place where you can get really big gains for things like these are especially tasks where you don't have enough training data to just train the model end to end and learn all the vectors for all the words in your vocabulary. So to go to unsupervised pre-training of word embeddings, this is a very brief summary. One thing that I think wasn't really extremely clearly stated in the reading, so I just wanted to reiterate here, is distributional versus distributed representations. So distributional representations are based on the fact that words are similar if they appear in similar contexts. In contrast, non-distributional representations are created from something other than just textual use cases. And the great majority of training word representations is done using just text, using distributional word representations. But there is actually a paper called Non-Distributional Word Representations by Manal Faruqui, who was here at CMU. And they trained it from WordNet. So then things that were in similar places in WordNet got similar embeddings. And another example of this is things like entity embeddings, where you have a big knowledge base that covers lots and lots of entities. It's possible to train these entity embeddings without explicitly using textual information. So that's a contrast between distributional and distributed representations. Distributional and non-distributional representations. And then distributed representations are basically something that we represent by a vector of values, each representing some salient feature of the word. And the contrast to this, which you often hear in like neural network literature, is distributed versus local. And local representations are basically representations where something's represented as a discrete symbol, such as a one-hot vector. So this is just some terminology. So are there any questions so far about this? Okay. So one interesting thing about distributional representations is actually that linguists, human linguists, use them as well. So has anyone taken like corpus linguistic courses or something like that? I see one or two hands. So there's a Python program in the word representations file called kwic.py. This stands for keyword in context. And basically what it does is you give it a word, you give it a corpus, and it outputs something like Pittsburgh. So Pittsburgh, along with all of the contexts that Pittsburgh appears in. And this is a very common thing for linguists to use to learn more about words. So this is called a concordance or a keyword in context search or something like this. And when you do this, you can take Pittsburgh, and then you can take Cleveland, and you can see that they kind of appear in similar contexts around them. So this is something that is useful for humans, and it's also useful for training our models as well. So count-based methods, you basically create a word context count matrix, count the number of co-occurrences, maybe weight them with pointwise mutual information to pull out like non-spurious correlations. Maybe reduce the dimensions using something like SVD, like we had in one of the quiz questions. And then you measure their closeness using cosine similarity, generalized Jaccard similarity, or other things like this. So these count-based methods, they're very efficient. They're easy to train, and conceptually simple. But prediction-based methods instead try to predict the words within a neural network, and word embeddings are the byproduct of this. And when we do these from language models, so you can get word embeddings just from language models. So if you remember our language model from our last class, we had two places where word embeddings came into our language model, like in the lookup matrices here, and the word embedding, the output softmax matrix here. But if you remember the keyword in context thing that I was talking about before, which founds the basis of count-based methods, they actually use a window all around. They don't just use the left context to predict. And empirically, this gives you better results, and it also makes it. It also has benefits of making it easy to calculate efficiently, et cetera. So the big kind of intuition behind word2vec or these prediction-based methods that use context windows is that the very first word embeddings were things calculated from language models, like an n-gram language model or something like this. But if you just give up on the necessity to actually calculate the probability of a sentence, if you give up on actually calculating a language modeling objective, you can make you can cut all kinds of corners that make things efficient and can just do the thing that results in the best representations. And this is true both for both for word embeddings and for contextualized word embeddings like Elmo and BERT. And these are also not language modeling objectives, but they're things, but they're good for training representations, and we'll be talking about those in a few classes. So as I said, this moves us closer to the context using count-based methods and are used in Word2Vec, etc. And the CBOW model basically predicts the word based on the sum of the surrounding embeddings like this, as you saw in the reading, but maybe a visual explanation is clearer. So then you might or might not take a softmax and calculate scores and get probabilities, and get a loss function. And I have an example of this in the code examples if you want to take a look. Whereas the skip-gram model basically predicts each word in the context given the word itself. So you calculate a probability over all of the words in the context given the current word, and calculate the loss function with respect to all of the words in the context. And you can also try that out as well. So so these are the two things kind of powering Word2Vec. They also power things like fast text, which was also written by Tomas Mikolov and others. So it's using the same kind of methods. The CBOW objective and the skip-gram objective are a little bit different, right? One is using the word to predict the context. The skip-gram, where the context, where in the CBOW objective, it's using the context to predict the word. In reality, like was written in the book, it doesn't really matter that much which doesn't really matter which objective you use. It matters more specifically like what contexts you're using to predict, or which contexts you're predicting, etc. And so that is that's a brief overview. I think this was largely in the reading. Are there any clarifications that people wanted to have?
So in the reading, it mentions that in the skip-gram, it assumes independence between each context word, and it turns out that skip-gram performs better. But why? Because it has an independent assumption, but it performs better. Why?
Well, so again, I don't know if it's a foregone conclusion that this always performs better. I think you see in some cases CBOW's a little bit better, in some cases skip-gram's a little bit better, but I think on average skip-gram is better. And as somebody who hasn't done a lot of work on word embeddings myself, maybe some other people have better intuitions, but my kind of intuition about this is this essentially has 4 times the amount of training data. So you're doing, in this particular case where your context window is 4, in this case you're solving 4 prediction problems, right? In the other case, you're only solving 1 prediction problem. You're solving the prediction problem predicting the center word given all the other words. So my impression is that my intuition is that that's probably the difference there, but I actually don't think the difference is that big empirically. So I don't know if anyone else has experience with this. No. Okay. Any other questions? No. Okay. I'll move on. So there's count-based methods and prediction-based methods. As shown in the reading, there's a strong connection between them. You can actually show that the skip-gram objective is equivalent to matrix factorization with PMI and a discount for the number of samples K, where we'll be covering the sampling next time. And this was actually a really, really interesting result, which says, like, people are saying skip-gram objectives are better. People are saying CBOW objectives are better. People are saying count-based versus prediction-based, when actually they're kind of optimizing the same thing. So as a result, it could be a peculiarity of the optimization method you're using, or the ability to scale things up to really large data sets, et cetera. So one of note is glove, and the reason why glove is a notable other method for word embeddings is number one, it is a number one, there are large pre-trained embeddings available that empirically work pretty well on lots of different tasks. But number two, it takes kind of a radically different approach. Instead of trying to do some sort of prediction with a neural network, it instead thinks directly of an objective that you would be good for, like theoretically good. And then it goes in, defines this using various operations on matrices, and then goes on to optimize the objectives. So the reason why I like this, the glove method, is basically it's very strongly motivated by like what they think should be good in word embedding models. And basically, it's a matrix factorization approach motivated by ratios of probability of word given context probabilities. And the idea behind behind why this would be useful is if you think about the most characteristic words with regards to something like ice versus steam. Like, what is the most characteristic difference between ice and steam? Probably the most characteristic difference is that ice is solid, whereas steam is not solid. Steam is gas. So if you look just at the probability of solid given ice, or the probability of gas given ice, you don't see a big difference. But if you look at the probability of solid given ice divided by the probability of solid given steam, you see this big difference between the probabilities. It's 8.9 times larger for ice than it is for steam. So the idea is basically these ratios of probabilities are a good way to come up with meaningful correlations, I guess. So they go through all these derivations from the start to a final loss function that satisfies these desiderata. So they start out with this function equal to the probability of ik given jk, where you add a bunch of desiderata, like being meaningful in linear space, being able to calculate differences in dot products, word context invariance. So unlike word2vec or something else, which uses different vectors for words and context words, glove uses the same vector for both. Also being robust to low frequency contexts, they are able to come up with basically this this thing here where it's wi transpose times wj, et cetera, et cetera, et cetera. And I forget exactly the details of what all of these things mean, because I wrote this down like a year ago and forgot to reread the paper before I did this lecture. But basically, the paper is remarkably clear about how they go from here to there, and I think it's a very nice thing to read if you want to have an idea how glove works. So this is one alternative to the prediction-based methods. And which one do people use right now? I think I'll talk at the end, but fast text is a very popular toolkit. It's a prediction-based method, but it also has a few extra tricks that are largely possible because of prediction-based methods. So because of that, I think glove is a little bit less popular nowadays, but it's also very nice to know this background. So the next thing to think about is what contexts do we want to use? And this is actually really, really important. So context has a much, much larger effect on the word embeddings that you get than the actual training objective as well, I think. And one extremely salient example of this is you have a small context window. If you have a small context window, you'll get much more syntax-oriented embeddings. So in particular, if you just take the two surrounding words as your context and train a skip-gram model, you'll get things that are very sensitive to like part of speech tags, et cetera. And then if you have a large context window, like let's say you took the entire document as your context, then you would get very topical embeddings. You would get things that aren't very closely related to syntax, but very closely related to topic. And another example is if you actually explicitly create context based on syntax, you'll get like more functional embeddings with words with the same inflection group. So this is something that's very important to think about if you're looking to learn representations of words. Are there any questions about this or clarification? Okay. So once we have embeddings, how do we want to evaluate them? I believe this wasn't covered super carefully in the readings, so I want to go into this in a little bit of detail. So you come up with and you train embeddings well. Then the question is, how do you know whether they're good or not? And in general, for any kind of like pre-training type thing, you have intrinsic, or not even just pre-training, but any type of kind of like language analysis task or representation learning task. You have two types of evaluation. One is intrinsic evaluation, where intrinsic evaluation basically says how good is something based on its features. Whereas extrinsic evaluation says how useful is it for some sort of downstream task. And in the end, probably if we're learning word embeddings, we actually don't really care if the word embeddings kind of look good that much. I can think of like one or two reasons why you would care. Like if you wanted to learn word embeddings and then visualize them and see like if you could learn anything from them. But most of the time you just want to use them in a downstream task. And the other thing is qualitative versus quantitative. So qualitative is examining the characteristics of the examples themselves and making some sort of subjective judgment about their goodness. Whereas quantitative is calculating some sort of statistics and maybe is more rigorous. So the first thing you can do is visualization of embeddings. So you reduce the high dimensional space into 2 or 3D spaces for visualization. In this particular case, this is an example of the word embeddings projected by PCA onto a two-dimensional space, which was just to show that there's like a consistent vector between China and Beijing, Russia and Moscow, Japan and Tokyo, et cetera. So if you go back to this categorization here, what kind of evaluation method would this be? Intrinsic and qualitative, yeah, because there's no way we can actually calculate a number of this. We just kind of look at it and say, hey, pretty. So as I said, the previous example was doing a projection of a linear projection from nonlinear, from high dimensional space onto a two-dimensional space that we can visualize. As humans, we can only really visualize and understand definitely two-dimensional spaces, maybe three-dimensional spaces if you have a nice browser or something like this. But it's also possible to do nonlinear projections that group things that are close together in a high-dimensional space. An example of this is Tisney, which is a nonlinear projection. And basically what it tries to do is things that are close together in the high dimensional space according to a Gaussian distribution should be close together in the low dimensional space as well. And so the idea is that you want to preserve the relative distance between them. And this is good in some ways. It gives you much more coherent projections. So for example, if you take all of the digits in MNIST, which is a famous digits data set of handwritten digits that I think most people know, and you just down project their values, you get something that looks like this. It's kind of a blurry thing where a lot of the classes group together. But if you do this with Tisney, you get this really nice you get this really nice nonlinear projection down to a thing where, things that are in the same class, digits in the same class are grouped. And this is basically, it's an unsupervised algorithm. You don't know the actual labels, but even so, it's coming up with a pretty coherent division of things. So this is a common technique for data visualization. And we have an example of using this on word embeddings in the code repository. It's not too complicated. But one thing that you should be aware of is that this type of visualization can actually be pretty misleading. Like most nonlinear things, like all of the neural networks you're going to implement in this class, this has hyperparameters. It only has a few. But based on the hyperparameters, you can actually take the things in the original space, run them through t-SNE, and adjust the hyperparameters and get things that look anywhere from this to this. Adjust a different hyperparameter, and you get something that goes from this into like even a helix that looks like DNA here. So basically, there's two things that you need to be very careful of. Number one, the hyperparameters for this matter a bit, and also just because you downproject something doesn't mean that linear correlations in the downprojected space are actually linear correlations in the high dimensional space. So if you really want to examine like word embeddings and find like whether the linear correlations that you're expecting hold, then t-SNE would be a less attractive like method for doing so. Are there any questions about this or verification things? So the place where I got these is also a link on the site. It's a publication in an online like blog/journal called distill.pub. And it's basically this thing where you can do like JavaScript visualizations and things within the journal. And it's very beautiful. You can go in and play around with it.
Just curious, what's the meaning of perplexity here?
Oh, the perplexity. The perplexity, I believe, if I remember correctly, is basically the one of the hyperparameters of the Gaussian, or like like either the Gaussian pre or post optimization. I don't actually remember. Does anyone know t-SNE better than I do? Yeah, yeah.
I think it might mean like the number of nearest neighbors that you consider, or the effective number of points that you consider to be the things within the neighborhood of a certain point. I think it's related to the standard deviation of the crossing, but I'm not remember.
Yeah, well, so I don't think it's the number of neighbors, but I think it's related. Your explanation of it being the standard deviation of the Gaussian distribution matched with what I remembered, but I think the better thing is to go take a look at the paper. Maybe you can tell me at the end.
The law actually says it's related to the number of things, but it's not that.
I think it's effectively related, and it's indirectly related by being like the standard deviation. But I'll like to make sure about that and check later. So that was so this is a first thing you can do. Whenever you have high dimensional spaces, you can kind of visualize them and do interesting things with them. I particularly like when you do these visualizations and you take the different classes and you color them different colors so you can see whether it splits things up into coherent parts of the space or something. There are also quantitative intrinsic evaluation measures that you can use to interpret representations. And one common one is relatedness or semantic similarity. And basically what this means is if things are similar in a embedding space, they should also be similar according to human judgments. So you gather a whole bunch of human judgments about words or whatever, saying how similar they are, and then you measure the correlation between the embedding, cosine similarity or some other variety of similarity and the human evaluation of similarity. Another thing is analogy tasks, where you try to find x for a is to b as x is to y. If anybody's taken the SAT test, it's the same, and you might actually be worried that word embeddings would be better at it than you are. I certainly would. And then also categorizations, where you can create clusters based on the embeddings and measure the purity of clusters. And then there's also something that's a little bit less common called selectional preference, which determines whether a noun is like a typical argument of a verb, for example. So of these, I think the fourth one is kind of rare. The first three are ones that you see pretty frequently. In particular, kind of the word similarity tasks of like correlation of relatedness and analogy are the ones that people use the most. If you want to do a human evaluation of whether embeddings are good, I think the third one's actually a good choice. And basically, this is you can do this using something called distractor tests, where what you do is you take 4 embeddings that are similar with respect to something, and then one embedding that is different. It's like one odd embedding that's out, like different from all the others, and then you try to see how often humans can identify the one that is the unusual one. So these are all good things to have in your toolbox of things that you can use to evaluate, and they're all explained in the reference. Then with respect to intrinsic evaluation, basically what you do is you take word embeddings and then you use them in your favorite downstream system. And this can be any system whatsoever. So you can either like initialize with embeddings, concatenate the pre-trained embeddings. You can also like multiply the embeddings by a transformation matrix. You can add a difference and regularize the difference. So there's all kinds of different ways you can use them. Then the question becomes, sorry, are there any other questions about like the evaluation metrics? Yeah.
I have one confusion about the extrinsic values.
Sure.
How do you concatenate the pre-trained values with learning specialties in substitution?
Oh, so the easiest way is if you have 300 dimensional pre-trained embeddings, you also add 300 dimensions worth of learned embeddings, and you just concatenate them together before feeding them into your classifier or LSTM or something like this. And then you only update the learned embeddings. You don't update the pre-trained embeddings. Yeah.
Is there any difference between the method that is used to measure the similarity, for example, the cosine similarity or Descartes distance?
So actually the method, that's going back to the intrinsic evaluation part, right? So like when you measure relatedness or for analogy tasks or something like this, using the cosine distance or the Descartes distance or some other metrics actually makes a really, really big difference in the final accuracy of the embeddings. Cosine similarity actually isn't the best method to do this. One of the reasons why it's not good, yeah, actually maybe I'll get back to this at the very end when we, the reason why I'll get back to this at the very end is because there are some other methods that I'll be talking about halfway through that'll be better illustrations of this than the one that I okay, no, actually no, I can explain it now. So basically, there's a problem with word embeddings called basically it's called the hubness problem, and the hubness problem is basically a problem that a single embedding is the nearest neighbor of many, many other embeddings. So an example of this would be you train a huge word embedding model, and because it's so big, it has lots and lots of last names in it. So because you have lots and lots of last names, you have embeddings for like John Smith and James Brown or something like that. So Smith and Brown are very, very common last names in English, but you also have less common last names in English, like Neubig, for example, being my last name, which I think is probably pretty uncommon. And so Smith and Brown are very likely to become hubs, and they basically pull in all the last names as their nearest neighbors. And so then when you do an analogy task, like A is to B as X is to Y, you're very, very likely to get one of those hubs. You're very likely to get like, let's see. Actually, a better example would be cities, like capital cities. So let's say London is a hub. So no matter which capital city you had, you would say Tokyo, Japan is to Tokyo as France is to something. And because London is a hub, you're very likely to get a hub. And so cosine similarity and other simpler metrics are very, very sensitive to this. So there are methods that explicitly consider this and use, one famous example is CSLS, which is, what's the abbreviation for? Something scaled local similarity. But what this does is it basically gets rid of this hubness problem. So even if your word embeddings are, it makes this embedding, this hubness problem better. So basically, even if your word embeddings are exactly the same, the specific metric, similarity metric that you use when you're doing something like an analogy task or a relatedness task actually has a big difference on the final output. And then if you want to evaluate different types of embeddings, then you need to make sure that you use the same similarity metric for every, like type of evaluation. Are there any other questions? Yeah.
Could you explain a little bit about the purity of clusters in the categorization?
Sure. So there's a couple ways you can measure this. One way is you already know gold standard clusters. So like, let's say you have WordNet, for example. And you know the WordNet classes. So you know like all animals are in one class. You know all cars are in another class. So then you know the gold standard clusters. And basically, measures of cluster purity can be calculated with respect to these gold standard clusters. And one example of them is how many things would you have to move between clusters in order to make 100% correct clusters. And then the measure of cluster purity, like the fewer things that you have to move, the better your cluster purity is. And then the second thing is the distractor tests that I just talked about. You have 4 embeddings that are very close together. And then you have one embedding that's kind of far from these. And you show all 5 of these words to a human and say, which one do you think is different? And then the success of the distractor test is basically how often, like what percentage of the time the person picks this one that is actually different according to the embedding space. So I don't think I have good, I don't think I have a reference for this specifically for the categorization things, but you can take a look at the reference on the website, and it should give you more like links that you can follow. Is that okay? Or?
Yeah, I just wonder, like, if an embedding of a word has many inherent features which will shift the, say, tomato can be vegetable and be fruit, and it will shift embedding to some way like.
Yeah.
Should the embedding, should the clustering be hard or soft? Because WordNet is like a soft cluster.
Yeah. And so another problem is tomato being a vegetable or a fruit is an interesting example, but I think banana being a fruit or a noun is maybe a more interesting example. So, like, banana is both a fruit and a noun, right? So, like, if you create an unsupervised clustering of, fruits and of words, and you get banana together with like lots of other nouns or something like that, is that actually a problem? Maybe that's okay. I think it's these kind of like clustering-based measures actually aren't super. It's not super clear what clusters you should use. Like how much does that tell you, and stuff like that. But evaluating unsupervised learning algorithms like word embedding algorithms is always difficult, but these are just some examples. Yeah.
two questions. The first is, most of these evaluations look at semantics rather than syntax.
Uh-huh.
So is there any specific way to look solely at syntax and focus more on that? And also, could you explain a bit more about selection preference? Where is that?
Okay, so could you look at syntax? I think the answer is definitely yes, you can look at syntax. To give one example of how people have done this in the past, not in the context of word embeddings, but rather in the context of contextualized word embeddings, which we'll talk about later. Basically, what you can do is you can take the representation and predict a part of speech tag or something like that. So in the case of word representations, you might want to predict, you might want to create a linear classifier that predicts the majority part of speech tag for that word. So if banana is a noun, 90% of the time you would predict noun. So that would be an easy way to do this. I don't know of any papers that do that explicitly, but there might be. Then the selectional preference thing, basically what this does here, I don't remember the exact details of this particular thing because I just read it through proxy in the Schnabel et al. Paper. But I believe what they're doing, selectional preference basically is, if I tell you that X barked, what would you think X would be? Like a dog, right? Or X meowed, that would be a cat, right? Is the subject. And then you could also have the object. So like the dog bit X, what would it bite? Maybe the man or the cat or something like that. So selectional preference is like what verbs can take certain things as subjects or objects. And I think basically the idea is they learn a vector from known verbs to known subjects, and then they see whether the predicted ones from unseen vectors correlate with the actual selectional preferences of those. So I'd have to go back and read carefully to make sure I'm not lying, but I'm pretty sure that that's what they do. Are there any other questions? Yeah.
I was wondering if intrinsic evaluations and extrinsic evaluations actually kind of agree with each other.
Good question. I'll talk about that next. So maybe I'll move on to that. So do intrinsic evaluation and extrinsic evaluation actually correlate with each other? And here is one evaluation that was done but in the Schnabel et al. Paper. And basically they have this evaluation over all kinds of different tasks, and you can see that for word relatedness tasks, CBOW tends to work better. For selectional preferences tasks, GLOVE tends to work better, or TSCCA tends to work better. For analogy tasks, CBOW tends to work better. So, kind of, you see, even on intrinsic tasks, there isn't strict agreement, which it makes sense. These are different types of tasks. And then if you go to extrinsic tasks, you can see that they evaluated it on chunking, which is basically a syntactic task where you try to chunk up phrases in a sentence. And they found that the Goldberg and Weston embeddings, which did really poorly on the intrinsic tasks, are actually doing the best here. So I think the answer will kind of rely on whether, for example, if they had a semantic downstream task, they might have had better correlation. But really, there's no one-size-fit-all embedding that works well for every single task. And I think there are trade-offs that you need to make there. So, actually, sorry, I already talked about this. But this is basically when we don't have very much data, is when embeddings are most useful. So up until now, this was kind of basic background on evaluating. There's been lots and lots of work on word embeddings. There's so much that I couldn't possibly cover all of it in the time we have allotted here. So what I want to cover instead is specific problems with word embeddings, specific kind of failures or things where genres where embeddings could be improved in general, and solutions for each of those. So Some of the limitations are that they're sensitive to superficial differences. They're also insensitive to context. So for example, financial bank and bank of a river. They're not necessarily coordinated with knowledge or across languages. They're often not interpretable. And also they can encode biases like stereotypical gender roles, racial biases, etc. And I will talk about each of these problems and some solutions in turn. So one really, really useful and kind of popular improvement to word embeddings recently is using subword embeddings. And basically the way these work is by taking not the whole word itself as a single thing that you look up, but rather taking some sort of subword, some unit that's shorter than the word and combining it to get the word in. The first example that I know of this was a morpheme-based embedding where basically they took, they split up the word into morphemes and then had this recursive composition of the word embeddings going from unfortunate into unfortunate, and then unfortunately into unfortunately. And because kind of morphemes are supposed to be the smallest meaning of unit, sorry, the smallest unit of meaning, smallest unit of meaning, you know, it kind of makes sense that you should be able to compose these these longer words from these morphemes. A much simpler method done by Wang Ling, who was here at CMU at the time, was running a bidirectional LSTM, which we'll talk about in a few classes, and then taking the representations from this LSTM and turning it into a word embedding. So both of these are reasonable methods. Both of these use neural net. Essentially, like on a high level, both of these are using neural networks to convert subword units, either morphemes or characters, into words. But the more popular method now is even simpler, and it's a bag of character engrams, which is used to represent words. And this was also done by John Weeding, who's now here at CMU. And basically what you do is you take the word and you split it up into character engrams, anywhere from length 3 to length 6. So you would have like beginning of word WH, WHE, HER, ERE, RE. And each of these character engrams would have its own embedding. And then you add all of these together for engrams from 3 to 6, and you get the final embedding of the word. And for more frequent words, you also add the embedding of the word itself. And this is something that you can train using a skepgram objective or whatever else like this. And the benefit of this is, number one, it doesn't require any linguistic analysis. Number two, empirically, it's very effective. I found it more effective than the bidirectional LSTM method or CNNs or anything else. And third, it's very, very fast. It's very fast to train because you're just summing things together. You don't need any matrix multiplies or things like this. So yeah, this is a very very nice method to use. Are there any questions about this? Or?
So,
yeah.
In the previous slide,
yeah.
Previous one, previous one where you were combining the two subword embeddings.
Sure.
Yeah, the left diagram. So I see here that morphemes are sometimes on the left, but sometimes on the right. So how do you determine that, or is there any intuition behind that?
So that's a good question here. I don't actually remember what they did here, but the you can come up with linguistic rules that would be pretty reasonable to do this. Like one example is you probably want to do things like derivational morphology before inflectional morphology, and what that means basically is derivational morphology. Probably the easiest and kind of like not 100% correct way to explain it, but the easiest way is basically derivation is something that more or less changes the part of speech tag. whereas inflection just adds like characteristics to the word while keeping the same part of speech tag. So like decide to decided would be inflectional, whereas dog to dogs would also be inflectional. Decidedly would be derivation. But anyway, so like you can you could come up with rules like this. I don't remember exactly what they used there. You could also just do all the things on the left and then all the things on the right. That would probably work almost as well for English. But, and we'll move on to the next one, where we have multi-prototype embeddings. So basically, the idea is that words with multiple meanings should have different embeddings. The example being like position. So position is an embedding, is a word that has lots of different meanings, and you would want it to be with different, have different word embeddings for each of these different meanings. So the way people did this up until last year, essentially was you would learn different types of meanings for these different embeddings, and maybe you would have a dictionary that says position has 4 meanings, and then you would have 4 different embeddings for position, and then you would decide which of them to use based on the context or something like this. But now I would say that probably these have been largely kind of replaced by contextualized word representations, which again we'll be talking about in a few classes. So this is maybe a little bit less relevant now than it has been, than it would be, last time I taught this class, I guess. You can also do non-parametric estimation, where you like decide the number of embeddings on the fly. So another thing that actually maybe is more relevant or more popular this year than it was last time I taught this is multilingual coordination of embeddings. And basically, we have word embeddings in multiple languages, and we would like the word embeddings in these multiple languages to match. So there's kind of 2 ways to do this. Sorry, I actually don't have them on the slide, so I'll write them on the board. But basically, the first way you can do this is you can train embeddings in one language, in each language monolingually, and then you can transform the embedding space of one language into the embedding space of another language. So I would call this like post hoc coordination of embeddings, or post hoc learning of bilingual embeddings. And then the other option is to learn the embeddings for the languages jointly, which means basically at the time when you're learning the embeddings, you basically learn them at the same time. So to give an example of post hoc coordination of embeddings, the model that we have here is kind of one of the first 2 models that was proposed for this, and they use a method called canonical correlation analysis. And what you do is you have your big monolingual embedding space sigma, you have your big monolingual embedding space omega, and for some subset of the monolingual embeddings, you have a dictionary that tells you that these words correspond to each other. And you run CCA, which basically tries to increase the correlation between these 2 monolingual embedding spaces by learning a transformation matrix, or learning 2 transformation matrices. And then you take these learned transformation matrices and you apply them to all the other embeddings, or to all the embeddings, even for the ones where you don't have dictionaries. And by doing this, you have a couple nice things. One nice thing is that the post-transformation embedding spaces tend to be better. So using this multilingual supervision actually allows you to improve your embedding spaces. In this example here, the embedding space on the top has kind of like good things and bad things are kind of mixed up and spread apart. Whereas after you do the multilingual coordination of the embeddings, you get all the nice things and all the bad things kind of separated apart. Another reason why this is nice is actually if you want to do multilingual training of an analysis tool, like a named entity recognizer or a parser or something like this. Having embeddings that are in the same space for both of these two languages is a good way to do this. And you can actually do things like take a part of speech tagger that was trained on English and directly use it on Spanish and get non-trivial, reasonable accuracy if you have these coordinated embedding spaces. So the another example of how you can do multilingual training of embedding spaces is basically this is by I'll try to put this on the references as well. I forgot to put this on the references. But the other type, joint training, is it was done by Wong et al. In 2015, and basically what they did was they took parallel data. So parallel data, you have data in two languages. You take word alignments between the words in the parallel data, and then with some probability, you just swap the words that are aligned in the two languages with each other. So you get something that looks like, I went to China in Chinese. So then you train on basically a corpus that looks like this, and because you're training on a corpus that looks like this, your embedding for the Chinese version of China will become close to the embedding for the English version of China. So this is a good method as well. Practically, which one do people use? People tend to use the former. The former being the one where you pre-train the embeddings monolingually and then train that and then coordinate them post hoc. And the reason why I think is because training embeddings monolingually or training embeddings in general is expensive. You want to do it on lots of data, and if you had to redo this every time you wanted to train bilingual embeddings, it would be harder. But that being said, I think ideally joint training should be better. It's more flexible. You have all the data at the time when you're training the embedding, so it probably should, in theory, be able to work better than post hoc coordination of embeddings. But you would have to come up with a good method that's reasonably fast. Yeah.
What's the downstream task typically for the joint training?
So I think there's two major tasks. So regardless for joint training or post hoc coordination of embeddings, it's cross-lingual transfer of analysis tools. Another famous one is bilingual lexicon induction, where you want to essentially learn a translation dictionary without actually having explicit translation dictionary data for that. So I think those are maybe the two biggest, and there's probably other ones as well. Yeah.
If you're learning it jointly and you're swapping out words, how do you tell? There are many languages with like similar words with totally different meanings. How can you tell which language that word is supposed to know?
Oh, okay. So that's a good question. So if you're doing joint training and swapping out words, how could you tell which language it's from? So if like I'm trying to think of a good example of this, but like it's the same spelling but different meaning in the two languages. One very simple way to do this that has been effective in previous work is you basically add underbar ZH, underbar EN, underbar EN, underbar EN. So you get a different embedding for the different languages. So that's super simple, but you could also come up with more sophisticated ways. Yeah.
So in the first method, do we manually? I suppose we need to manually align the two words.
Actually, no, and that's what I'm going to talk about next. So there's also methods for unsupervised coordination of embeddings. We can do surprisingly well learning unsupervised embeddings with no dictionary whatsoever. One example of how we can do this is by just using identical words. An extreme case of this is you only take digits, and digits, should be the same across languages. So you take all of the digits, you turn them into a translation dictionary, and you use this as a method for supervised training of word embeddings. An even more extreme method is just matching distributions. And what this says is basically we know that these are word embeddings. The word embeddings are from languages. And languages tend to have frequent words and tend to have infrequent words. And the types of frequent words and infrequent words they have tend to be similar. So, like a word for to, T-O, as in go to, is going to be very similar to, the word for to in some other language, because it's a common function word. And then, nouns are going to be less frequent and stuff. So, so one thing that you can do is you can then basically learn a transformation that matches the embedding space, matches the embedding spaces, and tries to make the embedding spaces look maximally similar to each other. And then there's a million different ways to do this. I believe the first one was proposed by Zhang et al. Using Earth mover's distance, which is kind of this distance metric over probability distributions, but there's lots of other examples of this as well. Another example of something that you can do with word embeddings is if you have specific training data, you can retrofit embeddings to existing lexicons. So if we have an existing lexicon like WordNet and we'd like our vectors to match this, you can come up with simple training objectives that basically, whenever things are synonyms in WordNet, you try to make them closer to each other. So if they're synonyms, they should have word embeddings that are closer together, and you learn some transformation function over these that tries to make the word embeddings similar to their original word embedding space, and also so that synonyms are grouped together. So this is a thing that you can use to inject external knowledge into word embeddings, essentially. Another thing is sparse embeddings. So what sparse embeddings are is basically each dimension of the word embedding normally is not interpretable. So what you do instead is you add a sparsity constraint to which says most of the dimensions in the embedding should be 0. So because most of the dimensions in the embedding is 0, the remaining dimensions are dimensions that should be more meaningful. And by doing this, you can kind of do these intruder tests where if you do the NNSE, you can look at the dimensions and see that they look more interpretable. I'm running out of time, so I'll just skim over the remaining things. So another big problem is, like a lot of our machine learning models are only as good as the data that we train them on. And word embeddings reflect biases in statistics, which could also reflect things like gender biases, for example. So this paper finds that lots of professions are very highly gender biased, and they also propose a method to kind of identify pairs that you would like to be unbiased and find a projection to try to remove this. And this is something that would be extremely useful if you're developing applications for something like where it's illegal to discriminate against people. Obviously we don't want to discriminate against people, but this would be one way, even if we want to reduce even if this will reduce classification accuracy or something like that, it's really, really important for us to be fair. This is a kind of good method here. I also heard an example from Dan Jurafsky where they basically trained word embeddings over time, taking newspapers from different time periods, and they had these really, really bad racial biases also, from newspapers in previous time periods. So this is something really important to think about if you're building actual applications. So finally, sorry, I'm a little bit over time, but I'd like to talk about this. Case study is the fast text toolkit. This is a widely used toolkit, maybe the most widely used toolkit here. How does that map into the things that I have talked about in this class? It's a toolkit in C++. It's fast and effective. It uses the skipgram objective with a character n-gram-based encoding method, like I talked about in the subword encodings. This is the base model. It's parallelized training using C++, so it's fast. You can run it in multi-threads. It also uses negative sampling for fast estimation, which I'll talk about next class. And it has lots of pre-trained embeddings for from Wikipedia or other data sources on many languages. So you can use these in many languages. So, yeah, sorry for going a few minutes over in class this time, but that's all I have for today.